Alright, today we're doing integration by parts, which is like the integral version of the product rule, actually. So the end goal is to be able to integrate a product somehow, but let's start with differentiating. So the product rule of differentiation is if you have two functions of x and you differentiate the product, right? So d dx of u times v will be u dv dx plus v du dx. And all we're going to do with this guy is we're going to move that v du dx to the left-hand side. And we're going to do that by subtracting it. Okay, so what you're going to end up with is d dx of uv minus v du dx equals u dv dx. And I've left all those ugly gaps there because our next step is to integrate everything we see with respect to x. And the most immediate thing to notice is that first term on the left-hand side. You're integrating the derivative of uv. And so what that's going to give you up to a constant, but it's all integrals anyway, is just the function u times v. Okay, because it's like the derivative and the integral cancel. Now be careful with that, they don't actually cancel. It's only true up to a constant, but we still have the integrals in the other terms of the expression, of the equation to deal with that. Okay, so that first term just becomes uv, and all integration by parts is we're writing this whole equation again. We're going to switch the sides where that first term has become uv. So the integral of u dv dx is equal to uv minus the integral of v du dx. Okay, and this is a method used to integrate products. Okay, and it's going to look a little bit weird because you'll see soon that it's not so easy to do straight away. You've got to make a choice of how you're going to split your product up. Okay, so let's color code everything and see what I mean by that. Because when we apply this, right, we have to make our choice of which one's u, which one's v dash. Okay, it's not like the product rule where it doesn't matter which way you do it. It matters which one we choose to be u and which one we choose to be v dash, because something different happens to them. Because look at the u, right? What happens to the u on the right-hand side is that it gets differentiated. Okay, so u appears, but also u dash appears. So whatever you choose to be your u term is going to get differentiated. Right, now if this is a little bit weird to you right now, go on because I think when we see an example it'll all make sense, right? I hope. But bear with me. What happens to the v? Well, it's actually v dashed on the left-hand side. Whereas if you look on the right, it's all just v. And so v dashed has been integrated. Right? So you can't avoid integration altogether. It's almost like you choose which piece of the product you want to differentiate and which piece of the product you want to integrate. And when you do integration by parts, it always begins with making this choice, right? Where you have a product, but one piece gets differentiated, the other piece gets integrated, and you want to see which one's easier. So watch this, all right? I've got an integral here where I've chosen u to be x and v dash to be sine x. Why have I done that? Because if I differentiate x, it becomes simpler. X becomes 1, right? Whereas if I integrate x, it becomes x squared over 2. I've made things worse. Whereas for sine x, well, it doesn't matter whether I differentiate or integrate. It ends up being much the same thing anyway. It's just cos x, whether it's a negative or positive, I don't really care, right? So because sine x integrates nicely and x differentiates nicely, that's how I'll choose to split it. That my x is actually the u function and the sine x is the v dash function. Okay, so I'm choosing to differentiate x and integrate sine x. So let's do that. Differentiate x, I get 1. Integrate sine x, I get negative cos x. Right? And once I've got those ingredients, I just use the formula and just be very careful with matching each of the symbols when you're using this for the first few times, but hopefully the colors are helping you see what goes where. So it's uv minus the integral of vu dashed, and that's what we get. All right? And so notice how u becoming u dash, the x becoming 1, made the integral step a lot easier. Right, so what we have is negative x cos x plus the integral of cos x dx. The negatives have cancelled. Okay, and that integral becomes easy. Integral of cos is sine, and so we have sine x minus x cos x plus some constant. Okay, so I think the hardest part here, the trickiest part, is making your choice of which one to differentiate and which one to integrate. And so you want to try and keep things as simple as you can. Often integrating is harder, so you want to sort of make sure you can integrate the thing you choose, make sure that it's an easy one to integrate, because you can almost differentiate anything, right? So make the integral easy, and where possible, make it so that after you've integrated and differentiated, what you end up with is something simpler to work with. Okay, and expect the first few times you do this, maybe you'll make the wrong choice. That's okay, just try the other way around and see what happens. Okay, all right. Another example, this is a little trick you can use to integrate things like this. Now we know when you differentiate log, you get 1 on x, but we don't know how to integrate log yet, right? What we can do is choose to see log of x as a product between itself and 1. So we choose v dash to be the constant function 1. And so u dash becomes 1 on x, and v becomes just the x, right? So we have this. Now, if we have that, then once again we can apply the form, and so we get this log x times x minus the integral of x times 1 on x dx. Again, just match the colors and see that that's what you end up with. Now the nice thing is, of course, the integral has suddenly become very easy. You have x log x minus the integral of just 1 dx. The x's have cancelled. All right, and the integral of 1 is just x, so you have this. Okay, so that's a little trick you can use. You can always try integration by parts using the constant 1 as one of your pieces of the product. Okay, maybe you can look ahead and see if multiplying by an x will do something nice like it did here. X times 1 on x became 1. All right, last one. This time, I'll show you sometimes you've got to use this twice to solve a single problem. So let's do an integral of e to the x cos x dx. So once again, you're going to make a choice. Which one do you differentiate? Which one do you integrate? Now, I think in this case, it might not matter too much, right? Because both of them differentiate and integrate fairly painlessly. So let's just say u is e to the x and v dashed is cos x. Let's just do it that way. Okay, so we'll differentiate the u, we'll integrate the v dash, right? And so we get e to the x for u dash and sine x for v after we integrate the cos. Okay, then our integral again is uv minus integral of v u dashed, and so we get this, match the colors again. And so, well, nothing much can happen here. We can just write it like this, right? And the integral isn't something we can do, but it looks awfully similar with the integral we started with, right? It's just that cos is now a sine, but there's not much difference between them, right? So actually, this is something that you might want to integrate by parts again. So I'll leave this one actually as an exercise for you to fill in the details with, because it's very similar to what we just did. Make u e to the x, make v dash sine x, and then apply the form. What you'll get is this. It's the same thing, except sines become cos pretty much. Maybe a negative here or there, right? And the special thing about this, right, is actually the e to the x cos x getting integrated is exactly now, not just similar, but it's exactly what we started with. And so actually, I itself features on that right-hand side. And so you can plus I to both sides, bring it across to join the I you've got on the left, right? And what you're going to get is this, where 2i equals e to the x sine x plus e to the x cos x plus a constant. And so I will be half of that, and that's your integral, okay? And so that's going to be your final answer. So sometimes you won't just apply this once, sometimes you'll apply it twice and get exactly the same integral appearing on the right-hand side, at which point you can collect it and divide to get your final answer. Okay, so that's integration by parts. That's all for today. Thank you for watching, and see you next time.